Welcome back to the deep dive. We're looking at the Mastering Cambridge O-Level Physics series.
And based strictly on the official new syllabus.
Yeah, so by showing the syllabus on screen, which they do.
Exactly. The mission today is simple.
Yeah.
Okay, let's move to the components themselves, the cast of characters in this play. Slide 2 acts like a map legend. We have cells, batteries, and switches. I noticed something specific here about the terminology. I usually say, pass me a battery, but the symbol for a cell is just one pair of lines, a long, thin one and a short, thick one. The symbol for battery is a whole row of them.
This is where physics gets a little pedantic, but for a good reason. A cell is a single chemical unit, like one AAA battery in your junk drawer.
Yeah.
Technically, that's a cell. A battery is strictly defined as a collection of cells connected together to provide more energy.
So a car battery is actually a battery.
Correct, because inside that box, it's usually 6 cells linked together. But your TV remote usually takes 2 cells, even though I'll call them batteries in casual conversation.
Got it. And the notes mention EMF here. Electromotive force. Is that just a fancy word for voltage?
Think of EMF as the pump. It's the energy provided by the source per unit of charge. It's the push that gets the electrons off the couch and moving through the wire.
And pressure in the pipes.
Exactly. Without EMF, you just have a piece of copper wire doing nothing.
And the switch is the gatekeeper. The notes say, open equals off, closed equals on. This always trips me up because in real life, if a door is open, I can go through it.
Right. You have to sort of invert your logic. In a circuit, the wire is a bridge. If the switch is open, you've raised the drawbridge. There's a gap in the road.
Traffic stop.
The cars fall off the edge. Traffic stops. You need to close the switch to complete the bridge so the current can flow.
That's a good mental model. Close the bridge. Okay, now let's look at the things that actually do the work, the loads. Slide 3 shows resistors, lamps, and heaters.
Yep.
But the really critical part of this slide, and I feel like this is a warning label, is the rules for the meters.
Oh.
The notes have this in bold, all caps. Ammeter measures current. Voltmeter measures PD. Must connect in parallel. Why is this distinction so lethal? Why can't I just plug them in wherever?
It's all about what you're trying to measure. Imagine a river. If you want to measure how much water is flowing, the current, you have to stick a flow meter inside the pipe. You have to be part of the flow.
In the pipe, okay.
That's a series connection. An ammeter is designed to have almost zero resistance, so it doesn't slow the water down. It just counts it as it passes.
Okay, so what happens if I hook up an ammeter in parallel? Say I treat it like a voltmeter.
Disaster. If you hook it in parallel, you're creating a shortcut for the electricity. Because the ammeter has almost zero resistance, the electricity looks at the light bulb, looks at the ammeter, and says, I'm going the easy way. All the current will rush through the ammeter. It's a short circuit. You'll likely blow the fuse in the meter, melt the wires, or at the very least, startle yourself with a spark.
Wow. So an ammeter is a toll booth inside the lane. You can't put a toll booth on the sidewalk.
Perfect analogy. And now look at the voltmeter. It measures potential difference. That's the change in energy between 2 points. It's like measuring the height of a waterfall.
Okay.
You don't jump into the waterfall to measure the height. You stand to the side with a tape, measure one end at the top, one end at the bottom.
You hug the waterfall.
You hug it. That's a parallel connection. A voltmeter has enormous resistance, millions of ohms, because it doesn't want to steal any current. It just wants to sample the pressure difference without disturbing the flow.
So ammeter sits in the line to count traffic. Voltmeter stands outside the line to measure pressure drops.
You've got it. If you mix those up, you either get a reading of 0 or, well, a puff of smoke.
High stakes for simple wires. All right, let's get into the mechanics of the flow itself. This is where the physics really splits into 2 worlds. Section 2 covers series circuits. Slide 4 shows a single loop. We have 1 battery and 2 resistors, R1 and R2, sitting next to each other on the same wire. The notes say, current is the same at every point. Why is that?
This is the single-lane road logic. In a series circuit, there is physically nowhere else for the electrons to go.
Right.
If 5 coulombs of charge leave the battery, 5 coulombs must pass through the first resistor, 5 through the second, and 5 must return home.
It's a conveyor belt. No getting off.
Exactly. So I total equals I1 equals I2. It's uniform. You can measure the current anywhere in that loop, and it will be identical.
But then slide 5 throws a curveball. It says voltage, the potential difference, is not the same. It says the total PD is shared between components.
Think of voltage as the bag lunch each electron is carrying.
Okay.
The battery gives every electron a lunchbox with, say, 12 joules of energy, 12 volts. As the electron walks around the loop, it hits the first obstacle resistor 1. It has to eat some of that lunch to have the energy to push through the obstacle. Maybe it eats 8 volts worth.
Okay, so it has 4 volts left in the lunchbox.
Exactly. Then it hits resistor 2. It eats the remaining 4 volts to get through that one. By the time it gets back to the battery, the lunchbox must be empty so it can get refilled.
So it's an energy budget. You spend a little here, a little there, but you can't spend more than you have.
Exactly. And if resistor 1 is really big, a huge obstacle, it demands a bigger payment. It takes a larger voltage drop. So in series, voltage is split based on how hard the components are to get through. V total equals V1 plus V2.
This explains why old Christmas tree lights are so annoying.
The classic example.
Yeah.
They were wired in series. If one bulb burned out, meaning the filament broke, the bridge was out.
The whole thing goes dead.
The current stopped everywhere. The whole string went dark.
And you had to check every single bulb to find the broken one. A nightmare.
And even if they didn't break, if you added too many bulbs to the string, they would all get dimmer because they all have to share that same 120 volts from the wall.
Oh, right.
The slice of the pie for each bulb gets smaller and smaller.
Which leads us to the rule on slide 6 regarding resistance. Adding resistors in series increases total resistance. The formula is simple addition. R total equals R1 plus R2.
It makes intuitive sense. Imagine you're running an obstacle course. If I had a second wall you have to climb immediately after the first one, your total time goes up.
Of course.
It's harder to finish the lap. You are adding hurdles to the same lane.
Okay, so series is the hard mode. Current is trapped in one lane, voltage is rationed out, and resistance keeps stacking up. Now, let's flip the script. Section 3, the parallel circuit. Slide 7. This diagram looks different. The wire leaves the battery, but then it splits. It looks like a ladder or a river forking.
The multi-lane highway.
Yeah.
This changes the rules of the game entirely.
The notes highlight a massive difference regarding voltage here on slide 7. It says, the PD across parallel branches is the same.
Wait, so they don't share the lunchbox anymore?
No sharing. This is the magic of parallel wiring. Look at the diagram. The top of resistor 1 is connected directly to the positive terminal of the battery via a wire.
The top of resistor 2 is also connected directly to the positive terminal. They both have a direct line to the supplier. If the battery provides 12 volt, resistor 1 gets 12 volts. Resistor 2 gets 12 volts.
It's like they both have their own private courier from the warehouse.
Exactly. This is how your house is wired. When you plug in your toaster and your TV into the wall, they are in parallel.
Okay.
The toaster gets 120 volts, the TV gets 120 volts. If your house were wired in series, turning on the toaster would make the TV screen go dim because they'd have to split the energy.
That would be unusable. So parallel allows for independent operation. But there's a trade-off, surely. Slide 8 talks about current. Current splits at a junction.
Conservation of charge again. Imagine a river flowing and it hits a fork. Some water goes left, some goes right. You can't create water out of thin air.
No.
So the total current leaving the battery is the sum of the currents in all the branches. I total equals I1 plus I2.
So the battery has to work harder.
Much harder. In a series circuit, the battery pushes one line of traffic. In parallel, it has to supply enough traffic to fill all the lanes. The more things you plug in, the more current the battery has to pump out.
And this leads to the most counterintuitive rule in the whole stack. Slide 9, resistance in parallel. The notes say, adding resistors in parallel decreases total resistance. I have to read that twice. Adding more stuff makes the resistance go down.
It sounds like voodoo, but go back to the highway analogy. Imagine a highway with one toll booth. Traffic is backed up for miles, high resistance.
Yeah.
Now, I build a second toll booth lane. Even if that new lane is narrow and the toll collector is slow, have I improved the flow?
Yes, you've given the cars another option. The backup clears faster.
Exactly. By adding a second path, even a difficult one, you are draining traffic from the main line. You have reduced the total bottleneck.
So every time I plug an appliance into a socket, I'm technically opening a new checkout lane for the electrons.
You are. You are lowering the total resistance of your house's circuit.
And because resistance goes down,
the current goes up.
Which explains why if I plug in a heater, a hairdryer, and a vacuum cleaner all into one power strip.
The breaker trips.
Right.
You lowered the resistance so much that the current became a tidal wave. The safety mechanism had to cut it off before the wires melted.
That is a fantastic takeaway. Series equals obstacles in a row. Resistance up, parallel equals lanes opening up, resistance down.
Spot on. The combined resistance in parallel is always less than the smallest individual resistor.
Okay, we've got the basic physics. Now let's look at how we actually use this to do smart things. Section 4 is called Control, Sensors, and Logic. Slide 10 introduces the potential divider. It looks like two resistors in series, and we are tapping a wire out from between them. The note 8 uses resistors to split voltage intentionally.
This is the bedrock of electronic control. Remember, in series, voltage is shared based on resistance. If I have a 12-volt battery and two identical resistors, they they split the voltage 50-50. I can tap into the middle and get 6 volts. But if I make the top resistor huge and the bottom resistor tiny, the top one eats up most of the voltage. Maybe I only get 1 volt out at the bottom.
So there's a voltage dial. By changing the ratio of the resistors R1 versus R2, we can manipulate the output voltage V out to be whatever we want.
Exactly. It's a ratio game. But it gets really cool when you stop using boring fixed resistors and swap one of them out for a sensor.
Which brings us to slide 11 and 12, the sensors. First up, the NTC thermistor. The graph shows a curve swooping down. The rule is resistance decreases as temperature increases. There's a mnemonic here. Hot equals low resistance.
NTC stands for negative temperature coefficient. It's strange because normal wires actually get harder for electricity to pass through when they get hot. The atoms vibrate and block the electrons.
Right.
But a thermistor is made of a semiconductor. When you heat it up, it releases more charge carriers, electrons break free, so it actually conducts better when it's hot.
Okay, so heat goes up, resistance goes down. And slide 12 is the LDR light-dependent resistor, the rule. Resistance decreases as light intensity increases. Mnemonic. Bright equals low resistance.
Same principle. Light photons hit the material, knock electrons loose, and create a path. In pitch black darkness, an LDR has massive resistance. It basically stops the current. In bright sunlight, it opens the floodgates.
So we have components that react to the world. Now, slide 13 puts it all together in an input sensor circuit. This is a logic puzzle. The scenario is it gets dark. We want a street light to turn on automatically.
Okay.
I want to walk through the logic chain here because this is where students usually get lost. Step 1, the sun goes down, light intensity drops. What happens to the LDR?
It's getting dark, so the LDR is tightening up. Its resistance shoots up.
Step 2, the LDR is in a series circuit, a potential divider, with another fixed resistor. What does that rise in resistance do to the voltage?
Go back to our series rules. The component with the higher resistance grabs the bigger slice of the voltage pie. Since the LDR's resistance is skyrocketing, it becomes a voltage hog. The potential difference across the LDR increases massively.
And finally, step 3. We have a lamp connected across the LDR.
Since the LDR is now holding a huge amount of voltage, that voltage is available to the lamp connected in parallel with it. The lamp gets the juice it needs, and click, the street light turns on.
It's amazing because there is no computer here. There's no code, no Wi-Fi, no server in the cloud. It's just the physical properties of the rock reacting to the dark.
It's an analog logic gate. If dark, then light. Pure physics.
It's elegant. But playing with electricity has risk. We have one last component on slide 14, the fuse. The notes call it a safety device.
The unsung hero of the circuit.
It's just a thin wire inside a glass tube. The text says, melts if current is too high.
It's a deliberate weak point. You know the saying, a chain is only as strong as its weakest link. In a circuit, you want a designated weak link. If a short circuit happens, like your toaster falling into the sink, the current spikes instantly. If you didn't have a fuse, the wiring inside your walls would heat up and catch fire. But the fuse is designed to be the first thing to die. It heats up, melts, and physically breaks the loop.
It commits suicide to save the house.
A noble sacrifice. And remember, the fuse must be connected in series on the live wire. It has to be part of the main road. If you put a fuse in parallel, the current would just go around it and it would be useless.
Right.
It's like putting a security guard in a field next to the gate instead of at the gate.
Position is everything. So we've worked through the whole stack. Slide 15 is the topic 4.3 summary, a cheat sheet. Let's do a rapid-fire recap for the listener to lock this in.
Let's do it.
I'll give the scenario, you give the rule. Series circuits.
One path. Current is the same everywhere. Voltage is shared. Resistance adds up.
Parallel circuits.
Multiple path. Voltage is the same across branches. Current split. Total resistance drops.
And the sensor?
Thermistors and LDRs. They translate the real-world heat and light into resistance changes. We use potential dividers to turn those resistance changes into voltage signals that can turn things on or off.
It's amazing how these few rules, just series versus parallel, essentially dictate almost everything in our daily lives.
They really do. It's the architecture of energy.
Here is a thought to leave you with, though. We talked about how parallel circuits lower resistance and series circuits increase it. We also know that computer chips, the processors in the phone or laptop you're using to listen to this, contain billions of transistors.
Billions. And they're all acting like tiny switches and resistors.
Now think about that engineering challenge. If those billions of transistors were all in series, the resistance would be infinite. Nothing would move. But if they were all in parallel, the resistance would be near zero. The current would be massive, and the chip would instantly melt into a puddle of silicon. So inside that chip is a microscopic city map, balancing millions of series paths and millions of parallel paths perfectly just to compute 2 + 2 without catching fire.
It's the ultimate balancing act, managing the flow so it's exactly enough to think, but not enough to burn.
It really makes you appreciate the invisible nervous system running the show. Thanks for diving into the world of circuits with us.
Stay curious.